Anyways, we're here to learn about WebGL today. Woo! What is WebGL? So I have a couple slides I'm gonna go through, otherwise we'll be doing code. But WebGL is basically just a 3D graphics library for browsers. Um, Normally, with like video games and stuff, you typically would use a game engine which does all this stuff for you. But when it comes to writing stuff in a browser, like using JavaScript, don't really have that luxury as much. But you can use WebGL, and there's a couple other like tools. There's some game engines even that are starting to come out that are meant for all web stuff. But for the time being, it's got a little manual. So WebGL just provides an interface to allow you to create and draw 3D things in space, and then just like you would normally in a normal desktop application. So that is what we'll be doing today. It's based on OpenGL, if you know what that is. So that's cool. Um, and just a disclaimer, this is not a complete tutorial. We're basically going to draw a triangle today, and it's just a starting point, just so you can kind of see how it works. Why are you shaking your head? Do you want to be here all night? Because we could get like a whole ass like lighting and like a teapot that's all around and like it would take all day, but with WebGL, we got a ways to go, buddy. Okay, so how does how do the graphics work? So this is a little important to kind of understanding how the code works. Um, and this is just in general. This isn't just WebGL. But typically, when you write code, normally you're writing it on the CPU. And this is with web development and with normal just coding in general. So you'll write code, and the CPU on your computer will take this code and handle it. And that's great. So with WebGL, we will use JavaScript, and then JavaScript will then you write all your code in JavaScript that uses WebGL, um, and then use another intermediate language for the shaders and stuff, which we'll talk about in a minute. Um, GLSL, so that's another coding language that's required for this. It's kind of similar to C, but like I'm just going to give you the code so you don't have to learn it today. But then eventually it sends that all to the GPU. So you use WebGL to send that data over from the JavaScript side to the GPU. And then the GPU will then take it from there and actually draw the stuff on the screen, like triangles and pictures or whatever. So a little more of a visual thing, which I'm not going to get too in depth on this. These are just pictures I found from Google Images, so you're welcome. Um, but Basically, what we're trying to do is take some data that's in 3D space, say that, or in our example, we're just going to have a triangle. But normally, say if you were to have a model or like a donut, like Adam was saying, um, you would have to somehow get that from that 3D space, the thing that humans can understand, and then somehow get that so it's in 2D on the screen, and have it in such a way that it actually makes sense. The way that we do that is what's called a render pipeline. And this is the basic render pipeline. You start with the element array, which is basically just all of your data. So say that we have a model of like Mario or something. Technically, he's made out of a bunch of triangles. And so all of those have different points. Yeah. If you have questions, let me know. I just
No, I was just concerned about Mario being made of
Well,
triangles.
everything, so yeah, everything that's 3D for the most part is made out of triangles. I mean, there's different strategies these days, but generally speaking, pretty much everything's made out of triangles. Um, a lot probably in modern games. In the older, like in Mario 64, which was like the first 3D one, he was probably not many, maybe not more than 100, I would imagine. Oh, maybe it was. But like modern Mario, probably like thousands is my guess. Because computers, um,
14,375 triangles.
yeah, exactly. Because back in the day when 3D triangles were first a thing, like they could only draw so many before the game would slow down. But like now, like Unreal Engine, their latest demo for Unreal Engine 5, they had like 5 billion triangles on the screen or something, and it still ran fine. A lot, yeah. So you can get really detailed, like rocks.
Original Mario was 838 triangles.
800, that's a lot more than I thought it would be. But I guess he's also like the main character, so you want him to look good. But basically, every triangle has 3 points in space, and you need to have that data. Um, And then we also have uniform states, which I guess I'm going to come back to talk about vertex shaders. So uh, with the WebGL stuff, we only interact with two parts of the rendering pipeline. We do the vertex shader and the fragment shader, and what those are in like English terms. The vertex shader just determines where those points are at on the screen. So this is how we, take that 3D data. It'll send it in, and then we can move it around if we want to, um, so that the computer knows where to do it, where to draw it. It takes over and does the hard stuff of actually figuring out where those pixels are and stuff for each triangle. And then once it has that part, it gives us the fragment shader, which we can do, and that's how we determine what color everything is. Um, so if we want to say like this triangle is red for Mario's hat or whatever, then we can do that. And the uniform states are like constants, data that we can pass in. So if we want to render a texture onto the screen, like a picture of me or something like, um, then that's you would be able to pass that in, and you can use those inside the shaders. So, any questions since I just kind of breezed through that? That's like a high level overview. Cool. Let's get to coding. Does everybody have VS Code installed?
Yep.
I assume that's like almost a prereq for this club. So here's the JavaScript, Adam, and
Just join the web dev server. Just join web dev to get this.
and there's the CSS. Second one was JavaScript. So the as far as file names,
Permission to send the web dev invite link into the game dev server.
yeah, that's fine.
Where do I send it in?
Just put it in the general chat. So open the folder that you have them all in. Yeah, if you have that installed, that's an extension. So if you don't already, isn't it just called like, yeah, supposed to be blank gray, yeah. Hold on, I forget the name. It was in the slides that I had. It's called Live Server. This one here. It's got like a purple. No, this one I've been using for years, so I don't want to hear it from you. Hey, by Richwick Day is the this one. So this is nice. It just starts like a server on your local device, and then like whenever you make changes, it'll automatically update. Um, and when you run it though, just make sure you have the index file selected. So we'll be doing everything in JavaScript. I am recording, yeah. So yeah, I basically gave you the index.html. This is just makes a canvas that covers the entire screen. So we're going to draw everything to the canvas. And then with the style.css, it just makes it so the canvas expands everywhere. Um, the JavaScript code that was given, uh, there's a couple functions in here. It starts out by just getting the canvas as well as the reference to GL, WebGL2. So that's a context that it uses. And then there's the resized canvas to display size. That's just like in case the screen resizes, we have to let WebGL know that we changed the size of the window that it's drawing to. Um, so that's just something I just left in there because I figured it wasn't going to talk about it too much. It's just there. And then inside of the render function, it'll check for a resize, and then it will tell the window to request another animation frame. So it'll just keep repeating this loop over and over. But the reason why we do it this way instead of using a while loop like you would normally do on an application is because of how JavaScript works, that would block the input, so it would just freeze the entire window. Whereas if we use the animation loop, which is built into JavaScript, it's like designed for this purpose, so it'll run that code once a update frame. And then this down here just starts the animation. So, um, Normally, if you were to like have a game or something, you have a moving object, you would want this. For our case, we could actually just delete this and it would work the same just because we're drawing a static image. But if you're doing something that's moving, you would want this. So let's get to the fun part. So how we're going to do this is there's going to be a few different parts. We have to set up a few different things. Uh, when it comes to converting like stuff from 3D space to 2D space, there's a bit of linear algebra involved. Uh, but luckily, that link that's in here, that is a linear algebra library that does matrices and stuff, so we'll be using that. But we need like a matrix for the camera so we can describe where the camera is in 3D space as well as um, its rotation and stuff. And then we will also need one for the object, and in this case, the triangle, so we can say which way is the triangle rotated, which way is it facing. So let's start by setting up the camera. So under the, I'm going to make this bigger too. Okay, that's more legible. So under the resize function and before the request animation frame, um, let's write some code that will set up the camera. We'll need a few variables that just kind of describe how the camera works. The first will be a field of view, which I'm just going to call FOV. Um, and we'll set this to, oops, I forgot the equal sign. 45 and then multiplied by math.pi divided by 180. So this is 45 degrees, which is like about normal, or sometimes people use 60 for video games. And that's just like how zoomed in or out does the camera seem. Usually in video games, you like change this dynamically, but in our case, this works fine. And we have to multiply it by math.pi divided by 180 just to get it into radians, because that's what it's expecting. We also need the aspect ratio of the canvas gl.canvas.client and then divide that by gl.canvas.client height. Um, and this is just so WebGL, when it renders things, it knows what the aspect ratio is, so it knows how to properly scale things in the X and Y axes so it looks normal and not stretched. We also need a near and far values. And what these are, yeah, 0.0. So what these are is when the camera draws things uh, in the 3D space, it has to have some sort of way to say, like, give a cutoff if something is too far away, because otherwise you just keep trying to draw things that are infinitely away from you, which isn't really possible because then the computer would just, get stuck. So at this point, we just say, like, as long as something is in between 0.1 distance from the camera and 100, then we will draw it to the screen. And especially if things are like 100 away or even 1,000, like that's pretty small. You wouldn't even see it normally. So at that point, you could just ignore it. And lastly, we'll have the projection matrix. And this is when we use that library. So we'll create a new matrix, which you do by mat4.create. And that'll just create a basic matrix, and then we will apply all of these values. What the projection matrix basically does is it takes this FOV, the aspect ratio, near and far, and it'll compile it into a matrix, which then the GPU will then use to know how to draw the camera and how to render everything according to that. So we can do that by using mat4.perspective, and then we can pass in the projection matrix, the field of view, the aspect, the near, and then the far. And it will do all the math so we don't have to, because that would be a pain in the butt. So then, in addition to having a matrix for that, we also need a matrix for the object we are drawing, in this case the triangle. So we'll make another matrix, call this like object matrix, mat4.create. And then this one, so just because by default, everything with a empty matrix is just at 0, 0, 0, like in the middle. So since we actually want to see it, we'll basically just move this a little bit, like away from the camera, so you can actually see it. We can do that by translating it. So we can do map4 dot translate, and then we pass in the object matrix, pass it in twice apparently, and then we will pass in an array as well, which has the values that we want to move it by. So I'm just going to do 0, 0.0, 0, 0.0, and -6.0. Um, so what this will do is the last value is the z value, which is forwards and backwards. So this will move it like away from the camera 6 units of space, and so that we can visibly see the triangle.
Wait, do we not like require anything from that form, or is that just like built in?
That's in the index. So
Okay.
yeah, you don't have to use require statements or anything. It should just load automatically when it runs.
Also, your aspect ratio thing, I think you had something in the backslash instead of the dot on the line.
Oh, you're right. Oops. I would have noticed that eventually. Thank you. Cool. Okay, so now we have those. Won't actually see them in use for a little bit, but that's okay. We'll use it later. Um, so let's start the actual like animation loop. That's just some extra data. Technically, you wouldn't have to always do this inside the render function, but you know, it's just here. Um, so let's clear. Usually, when you have a render loop, you always start with clearing the previous frame, just because like if stuff is moving around, you want to get rid of the old data. So you would do that by doing a couple things. First, we have to set the clear color to whatever we want the background to be, um, and a couple other things, and then we will clear, and I'll talk about those just as we go. So we'll start by setting the clear color, which is you do by gl.clearColor, and then you pass in 4 floats, which are just the value of whatever the background color you want it to be. So say that we want it to be black, or I guess we will do black here, because I think this is, yeah, I'm just going to do black just for simplicity. So that's 0, 0, 0, 1, which is red, green, blue is all zeros, and then the alpha is 1. I'd recommend just having the last one always be 1 if you want to do something different, just because that's like transparency, and I don't know how that works when it comes to the background. But so we'll do that. And then we also need to clear the depth. So what the depth is when it comes to drawing things on the screen is um, when you render stuff to the screen, you have 2 different images that it renders to. One is the thing that you actually see, which is like, you know, the triangle or whatever you're drawing, the objects. And then you have another one, which is the depth. And this just keeps track of like how far away something is. Because then when you're rendering stuff in 3D space, say that you have a cube at like 0.5 depth, and then you also draw another object, which is like a sphere. If that depth is further away, it won't draw it if it's behind the cube. But if it's in front of it that has a lower depth, then it will override the square. So that gives you that sense of depth and perception that you can tell that this object is closer because it's on top of the other one. But we also have to clear that every time just so it can reset. So you do that by clear depth, and we'll tell it to clear all of it by passing in 1. And just so, for some reason, with WebGL, you also have to activate things sometimes or enable stuff. Um, I don't know why that is, but just something you have to do. So we also have to enable the depth testing. Because I think you could just have it disabled, but then like if you have multiple objects, it might look a little wonky. And we'll do that by gl.enable gl.depthTest in all caps. And then we will also tell it what function to use for the depth testing, which we do by gl.depthFunc, and we pass in gl.lequal. And basically what that does is it says when it's comparing the depth, we want to do less than or equal to. So if two objects are at equal distance, or the new one is closer, less than like the depth is closer to the camera, then it will draw over. Which you could do something else, but then it would just look weird. So, and then lastly, we want to actually use that data to clear the canvas. So we will do gl.clear, and we will pass in two things: gl.color buffer bit. So this is telling it to clear the GL buffer just with the image data, the colors and stuff. And then we will use a single binary OR operator to combine these together. And we also do gl.depth buffer bit. So that'll tell it to clear both the colors as well as the depth that I just talked about. Questions so far? Lots of writing, understanding later. Okay, so now that we have that, we will come back to this in a minute. So now we actually need the shader code as well. So we can actually describe how it should render stuff. So these shaders are pretty bare bones. And this is just so you can kind of see what's going on. So we'll normally you would write a shader because it's a different language. You would write in its own like file or whatever. But like JavaScript has a lot of problems with trying to like load files, um, or at least I don't know. It's hard. But so typically for the sake of the example, I'm just going to write it in a string, and then it'll just load that string. So we're going to up above, below the GL canvas and stuff. Um, let's make this vertex source. Const vertex source equals, and then it's going to be a multi-line string, so I'm going to use the grave key to do that. Um, yeah, it's like the one in the top left of the keyboard. Yeah, yeah. So that's like a special one that lets you do this. Oh, semicolon at the end. Um, the first line of the shader code always has to start with the version or the type of like shader code that you're using, and we do that by doing hashtag version 300 ES. I can't exactly explain what that does, but no, just know that you have to have that in there, and that just determines, I think, what type of like syntax he uses and stuff because it changes a lot over time. Um, then we will also have something in vec4 a position. And what this is this is data that we're going to pass in. So this vec4 is the positional data for the triangle for each point of the triangle. And we can use that inside of this shader. We also have two other things. We'll have two uniforms. These are the constants. Uniform map4, we'll call this U object matrix. And then we'll have another one, uniform map4 U projection matrix. And these are the two, basically these are the two matrices that we created down below, but we're going to pass them into the shader and then use them in here as well to help use that linear algebra to determine where those points should be on the screen. And then down below, we'll define the main function, which is what's called by WebGL. So it'll be void main, kind of like a C program. Um, and then inside of here, we only need one line of code, and it uses a variable that you don't really like see in here, but it's called GL underscore position. And if you set that to something, that's what it uses in the other calculations to determine where the triangle is in the screen. So we will use that. So GL underscore capital P position, and we'll set that to the U projection matrix times U object matrix times A position. And what this is doing is this is basically combining all of those matrices and then multiplying it by the position. Um, I don't want to like go too in depth on it because it's just linear algebra. Um, but basically, we're taking that orientation data that's stored inside the matrices and we are applying that to the position of that position of the triangle. So say that we have the camera and it's rotated this way, and then we have the object, it's rotated this way and at this position. Then we need to multiply it all together so that like what that end result is basically going to be where it is in 2D space on the screen, more or less, or at least it is relative to the camera. So um, that's all we're going to do for that. That's the vertex shader. So that just determines where it is. And then we'll also have to write the fragment shader, which determines what color it is. So we'll do another, basically the same thing, put it in a string. We'll call this one fragment source with a grave. And again, same thing at the top, version 300 ES. And then there's something else that's a little different about this one. So we also have to add a line that says precision medium p float. And what this does is it basically tells the GPU what sort of precision to use for the variables. Um, Normally you wouldn't think about this, but uh, there's different levels of precision. You have like medium, high, and low, and that just determines how many bytes it uses per float. So low would be, I think, 2 bytes, and medium is 4, high is 8. And each one of these just gives you higher fidelity. So if you want something that looks really crisp and clean, you could use high, but that also makes it run slower. Medium is fine for most things. Low would be circumstantial. But you just have to put this line in here anyways. There's no default. So that just tells the GPU what precision we want to use. We also have an in vec4 color, or in color. I'm going to do in color. Or sorry, that should be out, not in. I know, I'm horrible. Out color. And that is it. We'll have an out color. So this is the color of the triangle, the color of the point of the pixels, I should say. So we'll have another main function inside of here, void main. And then this will set the out color to a vec4. And this is RGBA as well. So I'm just going to set this to red, which is 1, 0, 0, 1. Um, as to why the vertex shader uses GL position like a set variable, and then the fragment shader you have to specify the variable, I don't know why, but that's just how it is. Um, so high level overview of what these do. The first one just takes the positional data and it puts the triangle in the right spot on the screen, and then the second one makes it red. So okay, so now I should have given these functions to you as well, because this is just a lot of writing. I'm going to do that. Yeah, it'll be like that. So I'm going to give you guys some more code and then just paste it in here. Oh, wait. Oh, you even put my Discord server in there. That's so sweet. Cool. So put that in there, and then also there's one more. Just put it under the shader code that we just wrote. These are just a couple of functions. The key is just like the final product, like with all the code in there. So I just left that in there in case people wanted to see it. Did it let you download it? Oh. Yeah, because like that happened for everyone else. It said there was a virus and wouldn't let me do anything. And then like it turns out my file got corrupted on my computer, and I think that's why.
Because there's JavaScript in the file that there's a way you can trigger it.
Yeah, that's probably. Well, it threw a fit about the index file for some reason, but I don't know. I'm probably just gonna end up deleting that folder off the website just because it's useless. Next time I'll put it in a text file or something. But yeah. So just take these two functions and just copy paste them uh, in here. I did not copy like I said I was going to. So what do these two functions do? Um, the first one will create a shader, so it'll take in um, one of these sets of code, and it will tell WebGL that we're going to use this shader code. It will then compile it, just like you have to do with a C program. You have to compile this as well, um, and then it just checks and see if there was any errors, and it'll print them if there was. There shouldn't be, as long as you didn't have any typos or anything. Um, and then it will return it so we can actually use it. The second one will create a shader program. So this will take the vertex shader and the fragment shader, and it'll create a shader program. And basically what this is just that pipeline I was talking about earlier. The shader program is all of this combined together. So it'll take that vertex shader and it'll take that fragment shader, and it'll use those. So it'll actually take our data, input it, and then do all the work and draw it to the screen. So this is just like a helper function to do all that. I'm not going to make you all write it, so you're welcome. I figured I spent so much time on trying to figure out why the HTML file wasn't working. So, okay, let's move on. Let's actually create, so we have this function to create the shader program. Let's actually create that quick. Just up here is fine, I believe. Um, so I'll do const shader program equals create shader program. And we'll pass in the context for the GL as well as the vertex source and the fragment source in that order. And that will create that for us using all that code. At this point, if you look at the browser, you shouldn't have any errors. If you do, it'll be from it compiling that shader, or I guess if you refresh. Um, so if you see anything, just go ahead and fix that quick. Otherwise, it should be fine. Cool. All right. So under creating the shader program, I'm also just going to make a quick object to store some extra data that we're going to use. Um, I'm going to call this program info, and we will set this like this. And then inside of here, we're going to store a few variables. First is just the program itself. So we'll set it to the shader program like so. And then we're going to add also the attribute locations as well as the uniform locations. So up here, this is all the input data that we're going to give it um, into the vertex shader. We're going to pass in the attribute data, and the attribute data is basically just the stuff that's relative to the object itself, so like the position for the triangle points. And then the uniform data is those matrices. So these are the same for every point on the triangle regardless. Um, so those will WebGL automatically change all that stuff for us when it runs it. So I'm going to make another one. Just call it attributes. And that's another object. And then inside of here, we're going to have vertex position. And then we will get the location in the shader using WebGL, using gl.get attrib location. We'll pass in the shader program for the first argument, and the second one will be the name of it, which is a position. add a comma. Then we'll have the uniforms as well, same sort of format. The first one is the projection matrix, which we do in a similar way, except for instead of get attrib location, we'll do gl.get uniform location. Again, pass in the shader program for the first one, and the second one is the name. So this one is u projection matrix. And then comma at the end, and a second one, which is the object matrix. Set that to gl dot get uniform location again. Shader program and the name, u object matrix. So I'll give you a second to copy all that. Should look like that. This isn't like required, but this just helps organize things because this is what we'll be using to actually draw stuff, which is what we're going to do next. Okay, moving on. So let's move back to the render function after we cleared stuff. Now let's actually have it draw a couple things. Or at least start. I lied actually. Go back up. Um, let's just do that all at once later. So let's actually define the data for the triangle quick, just so we can get that out of the way. Um, the way that we do this is by creating the data on the JavaScript side. So we just make an array of like all the points on the screen. Um, and then we need a way to take that data from JavaScript and we need a way to pass it over to the GPU. So we do so by using WebGL to create a buffer, and that buffer is basically like shared data between the CPU and the GPU. So we can take it from JavaScript, put it in there, and then can then be used by the GPU in the shaders. So let's first create the buffer. Do const. Let's just call it buffer equals gl dot create buffer. And then we will want to tell WebGL that we're going to use this to put stuff into it. So we're going to do gl.bind buffer. And the first one is expects a constant just so it knows what it's binding. So we're going to tell it that we're doing an array buffer. Oops. Followed by the variable, which is the buffer. Next, let's actually define the positions for the triangle. Const positions equals an array. And I'm just going to organize these so a little easier to understand. The first point of the triangle we'll put at the top center. The second point we'll put in the bottom left. And then the third one will be bottom right. So the first one would be 0.0 or 0, 1, 0. I'm going to put this on a new line just as obvious which point refers to which point of the triangle. The second one will be -1, -1, 0. And then the third point will be 1, -1, 0. Those third values are just the z position. Those don't really matter because we're just making it really simple like 2D triangle. But if you wanted to make it like 3D, like have the triangle like stretch backwards or something, you would put that value in there too. Don't forget the semicolon, even though that doesn't matter. Lastly, we want to take that position data that we just wrote and we want to actually store it in that buffer so it can be used on the GPU. And we do that by doing gl.bufferData. Again, we want to tell it to use gl.arrayBuffer so it knows to use that. And then the way that JavaScript lists or arrays or whatever they're called works is like a little different than what it's expecting. It's actually expecting for the second argument a float 32 array. It's expecting a bunch of floats, and JavaScript doesn't store them that way by default just because of how types work. So we have to specify that we want this to be a float 32 array by putting it into that specific object. Um, so we'll pass in a new float 32 array and then put positions inside of there so that it actually reads it as floats with 32 bits. And lastly, we'll do gl.staticDraw, and that just tells WebGL that it wants the GPU to just use this for static drawing data. So this isn't going to be used for something else like an AI algorithm because you can do that in a GPU as well. This is for used for drawing stuff. And I don't know if that line of code is needed, so we're going to skip it. Okay, now let's go back to actually rendering stuff. Fun time. So first we need to tell it that we're going to use our shader program that we created. So after we cleared the screen, we need to say like, hey, we're going to use this program so we can draw stuff with it. And we do so by doing gl.useProgram. And we pass in, I'm just going to use programinfo.program for clarity. And then next we need to pass in those matrices that we created earlier so it knows to use that data. And we can do so by doing gl.uniform matrix for FV. Seems like an odd name, but basically there's a bunch of different functions. This one specifically is passing in a 4x4 matrix of floats. So we will pass in program info dot uniform locations or uniform, sorry, dot projection matrix. So that's saying that we want to set that projection matrix in the shader. We'll pass in false as the second argument because we are not transposing the matrix. And then lastly, we'll pass in the matrix itself, which is just projection matrix. And then we'll basically do the same thing for the other one. Just copy this line if you want to, and then we can change a few things. So instead of the projection matrix, we're going to pass in the object matrix. And do that again here too as well. So we'll set both of those matrices so that data is set in the shader so we can actually use this. This would technically only need to be done once, like this doesn't need to be done every frame, but we'll just do that here. And now let's also pass in the point data so it knows where to draw that triangle at. So I'll do gl.bindBuffer, and we'll again pass in gl.ArrayBuffer so it knows to use that array buffer, and then we'll pass in the buffer object that we created. And then we also need to tell it how to read that data. So it's one thing just to pass in a bunch of floats, but now we got to tell it how does it know how to map that data to this. So basically what the vertex shader is going to happen with this is that it's going to run it for every point, but we just gave it all of the points in one big float array. So we need to describe how it needs to split that up for the shader so it can run it individually. And we can do that by gl.vertex attrib pointer, and we pass in a bunch of arguments. The first one is similar to what we just did with the matrices. So we do program info dot attributes dot vertex position. We want to tell it that it is a size of 3, so it uses 3 floats. We also need to say the type. In this case, it is a float. That is what we passed in. So gl.float in all caps. It is not normalized, so it false. And then we just pass in 2 zeros at the end because those are things that we're not using right now. So just do that. And then again, like I said, have to enable stuff for some reason. So now we need to enable this array so it actually uses it. gl.enable vertex attrib array. Very long and wordy. And then we'll just pass in that first argument again. So program info dot attributes dot vertex position. So that'll just enable it so it can be used. Can't tell you why you have to do that. You just do. And last line, and then we can see if it works. This is so now that we've passed in all of the data, the last thing that we have to do is just tell it to draw it to the screen. And you can do so by gl.drawArrays. And we will pass in, the first one is the type of mode. So this is a constant gl.triangles, since we are drawing a triangle. The second one is the starting point in the array of the triangles that we're drawing. And the second one is how many points we're going to draw. So we'll pass in 0 and 3. We'll start at the 0th point, and then we'll draw 3 of them, which is the length of the array. Normally this would be like dynamic if you have a bunch of triangles, but we just have one. And after all that garbage, you should see a triangle on the screen. And if you resize the window, you should see it like automatically change as well, which is nice. But yeah, this is like the starting grounds for actually being able to render stuff. Um, Almost everything is made out of triangles, or at least with how modern graphics works for the most part. There's also other things that you might have heard of, like ray tracing. That's well, yeah, but still drawing stuff on the screen. Vector is a little different, um, but the only other way that I know is like ray tracing or some like cousin of it. But that basically is a little different. That one is where you shoot out basically rays of light from the camera, and then that's how you determine what color to draw. But the most common way is by using triangles.
So that positions array that we made.
Yeah, if you change that data, it'll change where the triangle is on this, or like how it draws the triangle. Yeah, that's a little out of the scope of this tutorial. But yeah, if I wanted to change
Hey,
this
I made the
position,
screen blue and the triangle blue.
but if I change this position up here to 2 instead of 1, like the top will be a lot more stretched out. And the way that you would like make it objects out of this is you have all the triangles like interconnect basically. So you have a bunch of triangles all placed next to each other. Like even spheres in video games are made out of triangles. They're just really small triangles. Yeah, they're not really spheres. There are every yeah. Yeah. Like Minecraft isn't actually cubes, it's actually just triangles.
How many triangles are too many for a model?
I was gonna do one other thing which I was gonna show off. That's why I said in earlier. So say that like you wanted to dynamically pass in data. Um, Thinking how to how do I do this? I don't know. I just do red. Um, like say that I wanted to pass in like I wanted to change the color of the triangle, but not directly in the shader. What if I want to update it from JavaScript? Um, you have to pass it. You can. You have to pass it through the vertex shader and then pass that into the fragment shader. So it's like a bit of handing off, but it does work that way. Um, or we could even change it so you can change it per point on the triangle. Let's just do that actually. So I'm going to do in vec4 and then I'm going to call this like a color. You don't have to follow along. This is just for sake of example. Um, and then this is going to be out vec4 out color. Set the in color. So this is basically this will automatically map to the first argument, which is this, and then we'll change this to in color. This is this will actually show something cool, which is what I'm going to do. So 0, 0, 0, 0, and this will be 0, 0, 0, 1. So I'm going to set the first one to red, second one to green, third one to blue. And then down here, I just have to tell it. I have to update this too. I'm going to add colors to each point in the triangle just to like show something.
Oh, you doing the thing we did in class?
Yeah, the thing that we did in class. I think I called it A color, right? Yeah, I did. This, and then down here, you have to copy this line. So this one, I think I actually need to use the offset values. Stride 0, offset 3, question mark? And then does this need to be 6? I don't even know. We'll find out. Does not match any vertex varying. Oh, it's not supposed to be. I forget how this works. It's not out, is it? Is it varying? Is this varying?
No. Oh, sorry, green plus blue. Wait, what did I say? Blue plus yellow equals green. So how does red plus green equal yellow? That doesn't make any sense.
What does it mean it doesn't match it?
This doesn't match.
Oh yeah, but why?
Did you make the colors or separate?
Oh no, I added them to the same array. I mean, this is like completely optional at this point. I'm just messing around, but yeah, that's what I made it. Maybe I should make it a. Hmm. Oh no, that should be fine.
Considering you did all of that for one time, is there some mad lad out there who coded a whole character model by just coding it out?
I wouldn't be surprised if people used to in the old days, like Mario 64.
Let's be honest. The dude who made the roller coaster probably did.
Yeah, he probably did. Yeah, exactly. The bro literally coded everything from the assembly. That's nuts, man. You, yeah.
I feel like the time it would take you to make that would like mean that computers would evolve past the point of needing to do that. But I don't know. I guess
It was. He claimed that he wanted it to be like super efficient for his game, but honestly, the man could have written it in C and it would have been probably the same. So I'm supposed to use varying.
Okay, I was thinking this is a crazy concept. Triangles. I know it's probably crazy, but still.
Makes me
The
Hmm.
max triangles for the average mobile device is 500,000.
Yeah, that makes sense. Yeah.
That's a 500,001 model.
Maybe that's why I'm
Let's look at my
No.
classwork.
It'd be fun. I thought it would catch on fire and it would just pop the battery. Yeah. It turns into emergency eject.
Varying vec 3. Maybe I need to pass in a vec 3.
Well, you're
Hmm.
messing with that. You want to announce our election results.
Oh, okay. Remember?
No, I was reading the response.
Our president.
Yay.
The next required position for us to stay above is treasurer. So our treasurer is Isaac. Our vice president is also Isaac.
Yeah.
Our webmaster is also Isaac.
Man of many,
And our
many
student
talents.
outreach is there we go. Now you have to run Clubfest. Good luck. That's like the only thing student outreach does.
Clubfest is fun.
Yeah, you like you just stand around
The whole day.
like
See, I make the entire club do it, so we don't have a position for it. All of our officers have to help with Clubfest.
That's what
As a
I'm
president,
here
you
to.
now have the responsibility of taking care of this.
Thank you. Wait, don't we have a closet?
No. Oh, I also will give you the trifold.
Yeah, ours is our award from last year is probably just gonna sit in our locker because I emailed our advisor and he's like, "Oh, I'll find somewhere for it." Never got back to me.
We got our locker taken away.
Why?
What the heck? For
Yeah, we never had locker anything. You're lying.
yeah, I know. For E-Week, you guys are doing because we burned down Marston a little bit.
It
wasn't us. It was freaking Fly. Stupid
Was it?
freshman.
what?
Was it?
Yeah, that's what I was told.
Oh, I thought it was.
Wait,
Man,
it's
how
out
many
now?
times have these guys been responsible for ours?
I didn't know it was
No,
common
no,
knowledge.
Fly. Freshman leaders in engineering. Those little
Oh, fly.
gremlins.
I thought that was like a nickname for
No,
like.
no, 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 no. Those little gremlins burned down Marston. I was told Fly, but like unsafe batteries.
I thought sweet.
That was really cool and also awesome.
So
I was told it was between sweet and Hispanic engineer. So this was the morning.
but you guys should also come to the next CSC meeting. I think there's one more.
I think so, yeah.
So, what do I do with my P card? It's just
I think it just
like-
expires or something, doesn't it? I mean,
What that did.
No. That's what the last person did to me.
I just never.
Are you still recording this, by the way?
Oh yeah, yeah. I could probably stop doing that.
Because I think my pleasure about to move on to the second evolution of the night.
Go forth, make games be awesome.
Yeah.
What I missed, but yay!